Welcome to using your cluster job scheduler on your Alces Flight Compute cluster. Before we get started, you'll need to have an Alces Flight Compute cluster launched on AWS, and you'll need to have SSH access to that environment. So why do we need a job scheduler on a personal HPC cluster? Well, there's a number of reasons why having a job scheduler available can help you to make the best use of your HPC resources. For example, it allows users to submit jobs for processing and come back to them later. That means you can keep your cluster busy overnight or over a weekend when you're not at work. A job scheduler also allows Flight to auto-scale your cluster to meet your workload. By watching the scheduler queues, Flight can automatically deploy compute nodes as and when you need them and shut them down when they're not being used. It can also help to orchestrate launching of parallel jobs. The integration with most popular MPIs and the job scheduler allows the scheduler to tell the MPI exactly which resources are going to be used for your parallel job. Lastly, it's great to train users in best practice, so jobs that have been launched on a personal cluster can also be run on a shared HPC cluster, for example as an on-premise device. Alces Flight comes with the Open Grid Scheduler job scheduler. Open Grid Scheduler derived from the Sonning Grid Engine codebase, so syntax is virtually identical to SGE. Anybody who's used to using SGE should be able to move on to Open Grid Scheduler relatively easily. Open Grid Scheduler is open source with lots of contributors, and it's free to download and use. As an open source application, please consider acknowledging the scheduler in any copyright or any research work that you publish. Grid Engine is very stable, it's a well-established job scheduler, and there's a commercial version also available if you do need support. To be able to submit jobs to the job scheduler, you need to identify what type of job you're going to be running. Let's look at three of the most common types of jobs now. The most common type of job is a serial job. Serial jobs use a single CPU core for their processing and may be submitted to run on any CPU core in any compute node of your cluster. Sometimes people might want to run a lot of serial jobs together, and that's called a task array. The second type of job is a multi-threaded job. This is using multiple CPU cores on just one node of your compute cluster. A lot of software falls into this category these days, and users must tell the scheduler how many cores they want to use when they submit their job. The third type of job is a parallel job. This job uses two or more compute cores on a single node or multiple nodes across your cluster. Most parallel applications use a message passing interconnect or an MPI to achieve this. Again, users submitting parallel jobs must request the number of cores that they want to use across the cluster. It's the job of the job scheduler to run all these different types of jobs across your compute cluster. They are different shapes and different sizes, and the scheduler has to work out which job's going to run next based on what you've requested the job needs and also what resources are available to you. In addition, the jobs you submit may be of interactive or non-interactive type. Let's look first at interactive jobs. Interactive jobs are started on the scheduler using the QRSH command. An interactive job can be serial, multi-threaded, or parallel. The input data for an interactive job is the user interacting with the application either on the command line or in a graphical desktop session. Similarly, output data is shown on screen. There's no file record of the output data from an interactive job. Let's look at launching an interactive job from the command line of your cluster. Use the QRSH command to request an interactive job session. The scheduler will automatically start your job and log you onto a compute node if you have resources available. On a compute node, I can run whatever application I want. For example, here, let's run the memtester application on my compute node. When I finish my interactive job, I can just use the logout command to return back to my login node. I can also launch an interactive job from a graphical desktop session. From the Applications menu, select Terminal, use the QRSH command to request an interactive job. I then get logged onto a compute node by the scheduler. I can then use my application. Here I'll run GLX Gears, which is a graphical application. Although the application is running on the compute node, the graphical session for that application is forwarded back to my remote desktop session on the login node. The most common way for users to use their job scheduler, however, is by submitting batch or non-interactive jobs. Batch jobs can be serial, multi-threaded, or of parallel type, and they're submitted via a job script. A job script is a list of commands or instructions to the job scheduler to be able to run your job. The scheduler transmits that list of instructions to your compute node and then executes it on one of the nodes of your cluster. Job scripts can also contain instructions for the job scheduler to explain how you want your job to be run. Once your job script's written, it's submitted to the scheduler using the qsub command. Job output is written to a file on your cluster for you to look at after the job has run. Let's look at writing a simple batch job script and submitting it to the scheduler. From your command line login in Linux, use a Linux editor to create a script file. I'm going to use nano, and I'm going to call my job my first job. Job scripts start with the interpreter that you want to use. In this case, we'll use bin bash, and we'll use the -l parameter to specify we want a login session for our job. It's going to be a very basic job, so I'm just going to say a few echo commands. Hello from hostname, that'll tell us the machine the job is running on. I'm going to tell the system to go to sleep for 30 seconds, and then I'm going to say goodbye from my job. I'm going to save that, Control X in Nano, and there's my job script that I've just written. We can submit that job script using qsub and my first job script, the name of my script. The scheduler immediately comes back and tells us our unique job ID. This is my job ID number 17. Job IDs are used only once on the cluster, and they're never replicated for a particular flight compute environment. I can use the qstat command to view the status of my job on the cluster. Here I can see job ID 17, the name of my job, my username, the state of my job. R here is for running. You might also see jobs in QW for queuing and waiting status. And over here we can see this is the name of the compute node that my job is running on. Now it's a batch job, so I can't see what the job is doing, but as we said, the job will be writing output to a file in my home directory. If I use the ls command, I can see the output of the job has been stored in this file, which is the name of my job script, a .o for output, and then the job ID for my job. If we take a look in that file, we should see the output for my job. So here is where I echoed the command and then the host name. Here is the goodbye after the job's completed running. If I do another qstat, the job should have finished by now. Yeah, the job's gone from my job queue. So that's the first job, very basic one, that we've run on our compute cluster. Now both qsub and qrsh can also receive instructions from users about their jobs. Common instructions include control over your job, so things like providing a name for your job so you can find it later, controlling how the output files are written in a batch job, informing the scheduler when to run your job, and requesting additional resources for your job, for example, more CPU cores, more memory, or maybe a longer runtime. Let's look at some examples of how you can give instructions to the scheduler about your jobs. For example, I can use a parameter, which is -n, to give my job a name in the scheduler. So if I wanted to call my job job1, I can submit the same job script with a -n. I then run qstat, it will show me the name of the job that I gave it. Alternatively to putting parameters on the command line, I can also embed scheduler instructions in a job script. So using my editor, I can edit my job script again. Job script parameters are added using a special line indicator that starts with a hash and then a dollar. I can then use -n for name, and I can give it a name job2. Saving that job script and then submitting it, the job scheduler will automatically pick up the job name that I provided for the script. Another useful feature is instructing the job scheduler where to store the output from my particular job. The job scheduler directive for that is -o for output and then a file name of where to put the job. We can add that again on the command line, or we can add it, as this example here, using the $$ line in my job script. The variable $job_ID is automatically set to my job ID number. This means that I can submit the same job script many times with output files going to different files on my file system. For example, here I've modified my job script to include the -o parameter, $home, that's my home directory, a file name, and then a $job ID at the end. When I submit this script, the scheduler will immediately tell me again the name of my job and the job ID that it's got. The output file is stored in my home directory under the name myjob2.out with the job number at the end. In this way, you can run the same job script over and over again, each creating a different output file. It's important to make sure that the directory that you'll be writing your output file exists before you submit your job. Users can submit task array jobs using the -t parameter. -t is provided with both a start and an end task number for a particular job. In this example, we've used -t 1 to 100. The special identifier $task_ID is filled in automatically by the scheduler with the current task ID of the running job. For example, here I've modified my job script to include the task ID parameter, -t 1 to 100. The rest of the settings are the same, but I've also edited the output file location to include task ID. Running the qsub command on that task job automatically tells me my job number is 23, I'm running tasks 1 to 100. I can use the qstat command to view the jobs that are currently running on the cluster. Each one of the running tasks will create its own output file. Here you can see task job 23, tasks 1 to 20 odd running at the moment. The scheduler will automatically cycle through all of the tasks in your job until they're all complete. Each one will create its own task output file. When you've finished running your job, it will automatically be cleared from the scheduler system. If you want to clear a job earlier, you can use the command qdel. Qdel will immediately stop your job and clear up any resources that that job's been using. Parallel jobs can take a short while to delete. Once they're deleted, they'll disappear from the qstat output. By default, the job scheduler allocates default set of resources to the jobs that you want to run. For a flight compute cluster, a single job will be allocated 1 CPU core, up to 1.5 gigabytes of RAM, and a maximum of 24 hours runtime. These limits are automatically enforced, but users can request different limits if that's required. For example, to request more memory for your job, you can use the parameter -l h_vmem and then the amount of memory that you need. Jobs requesting more memory may queue for longer or need larger instance types in order to run. Memory limits are automatically enforced by the scheduler, so exceeding those limits will mean that your job is stopped. This happens to protect your compute nodes and make sure that your cluster keeps on running. The default runtime for your job is 24 hours. That's measured by slot occupancy, so the time when the job starts to when it's due to stop. You can request more time by using the -l h_rt for runtime, and then putting hours, minutes and seconds after that. The example on the screen shows requesting 48 hours for your job. The amount of time you request is a maximum runtime. Your job will be accounted for if it finishes early. Time limits are automatically enforced by the scheduler. Any jobs exceeding their limit will be stopped. Users wanting to run multi-threaded and parallel jobs need to inform the scheduler of the number of CPU cores they want to use. The scheduler uses a parallel environment setting that must be requested by name, along with the number of slots or CPU cores that the user wants to use. Your Alces Flight cluster comes with 3 parallel environments already set up. They are the SMP parallel environment for running multi-threaded applications on a single node, the mpislots parallel environment that runs MPI across multiple nodes, and the mpinodes parallel environment that allows users to select how many individual nodes they want to participate in an MPI job. When requesting the SMP parallel environment for multi-threaded jobs, use the -PE setting, SMP or SMP verbose for more informational output, and then the number of CPU cores that you want to request for your job. For users running MPI jobs, they can use the mpislots parallel environment. That's requested with -PE, mpislots, and then the number of compute cores that you want to run for your job. Remember that memory allocations are performed per job, so requesting 4 CPU cores will give you a total memory requirement of 6 GB by default. The mpinodes parallel environment allows users to request entire nodes for MPI jobs that prefer to run on dedicated hosts. Use the -PE mpinodes parallel environment with the number of slots or complete nodes that you want to allocate to the job. Memory allocations are performed to allow all of the memory in the compute node instance included in the job to be used for your parallel job. To allow users to get started as quickly as possible, Alces Flight includes a number of job script templates for each of the different types of jobs you may want to run. Use the Alces template command to show a list of the templates that are available on your cluster. For example, on my cluster, I can use the command Alces template list to show me all the templates that are available. I can then use Alces template copy one of these template names to a job script of my own. Let's create a MPI slots job. Type in the name of the template and then the name of the job script, my MPI job.sh. Flight will create a new job script for you. I'll use the nano editor to take a look at that job script. Each of the different types of directives is included with a comment explaining what they do. You can review the script, you can change the job directives as you need them, then at the end of the script add the MPI run command for the application that you want to run. Take a look at some of our example videos and some of our tutorials online for a view of what MPI jobs you can run on your cluster. Here, I'm just going to change the number of MPI slots I'm running from 2 to 8. I'm going to save my job script, and then I'm going to use the qsub command to submit it. Grid Engine will tell me my unique job ID, number 26, and shows me that my job is running. The output file for my job script is in my home directory in this file here. Because I used the MPI slots verbose setting for my parallel environment, I get this output at the top that shows me some information about how my job was scheduled and run. A host file for my MPI job has automatically been created by the scheduler. The output file for my job is saved in this job script. It's a fairly simple job. It just outputs a message from all the threads that run the job on the cluster. Use the Alces template list command and copy commands to generate your own job scripts based on the template provided. As well as details on how to run your application, your job scripts can also contain job scheduler instructions that tell the job scheduler how to run your job, module load and module unload commands for making applications available in your job. You can also include storage preparation and management tools, Alces Storage Get and Alces Storage Put. This can help you to check in the result files from your job back to your S3 or Dropbox environment as soon as the job is completed. Take a look at our other videos and our online tutorials for examples on how to run some of these commands. That concludes this video. Please watch the other videos in the series for more information about using your cluster and running applications through the job scheduler. To find documentation online, just go to our website, alces-flight.com. Click on the documentation link. That will give you all the printed documentation for using the system.